Somewhere in your house, there's a spot on a wall with 2 or 3 patched holes in it, an inch apart. Maybe there's still a hook screwed in next to them, sitting a little crooked. That's the archaeology of drywall anchors. You put one in, it held for a while, it got loose, you moved over an inch and went a size up. And every one of those holes got drilled on the same assumption, that the fix for an anchor pulling out is a bigger anchor. I'm a carpenter, so my instinct is to get into a stud. But there's never a stud where you need one. And if you want a row of hardware across a wall, hooks, clips, brackets, the studs are 16 inches apart and your hardware isn't. That's exactly when people reach for anchors, and it's exactly what anchors are worst at. So how do you do it? There's a fix that costs a few dollars and takes about 15 minutes, and almost nobody outside the trades talks about it. It'll land better if you know why anchors fail first, because that's the part that points straight at what to do instead. When a drywall anchor lets go, the anchor is almost never what failed. The wall failed. Here's what's actually behind it. Half-inch gypsum board is a slab of hardened plaster with a sheet of paper glued to each face. The plaster is decent in compression and almost worthless in tension. It has essentially no ability to resist being pulled apart. The only real tensile strength in that panel is the paper. That's it. That's the material every anchor in the store is trying to hold on to. There's a standard test for this. It's called nail pull resistance, and it measures how much force it takes to yank a 1/4-inch nail head straight through a panel. For half-inch board, the spec is 77 pounds. That's the paper tearing. That's your whole wall in one number. So look at the package on a heavy-duty toggle. 238 pounds in half-inch drywall, which sounds like it beats 77 by a mile, and in a sense it does. A toggle works by getting a steel bar behind the panel and spreading the load over a couple of square inches instead of concentrating it on one screw head. That's real engineering, and it genuinely helps. But there are two things about that number that nobody puts on the front of the box. The first is direction. Anchor ratings are usually published as shear values, the load hanging straight down, flat against the wall, gravity pulling parallel to the surface. Tensile is the other number, the one that measures pulling straight out of the wall, and it's always much lower. Marketing departments quote whichever one is bigger. The second is safety factor. That published figure is a laboratory result. It's the load at which a fresh anchor in perfect board finally lets go. The convention in the trades is to work at about 1/4 of a tested ultimate. So that 238-pound anchor is realistically a 60-pound anchor, in shear, in undamaged board, installed perfectly, with the load hanging flat. And almost nothing you actually want to hang meets that description. But here's the part that really gets people, and it has nothing to do with the anchor at all. It's leverage. The instant something projects out from the wall, it stops being a hanging load and becomes a lever. And that lever is trying to peel the top of your hardware off the wall. Take a coat hook, bracket 2 inches tall, screws top and bottom, hook sticking out 3 inches. Hang a wet coat and a bag on it, call it 20 pounds. 20 pounds times 3 inches is 60 inch-pounds of torque, resisted by 2 fasteners 2 inches apart. The bottom screw gets pushed into the wall. The top screw gets pulled straight out with 30 pounds of force. 20 pounds of coat just became 30 pounds of tension, in the exact direction drywall is weakest. Now do a shelf. 40 pounds of books on a 10-inch deep shelf, bracket plate 5 inches tall. 40 times 10 is 400 inch-pounds. Divided by 5 inches of fastener separation is 80 pounds of pull-out on the top fastener. Your 40-pound shelf just doubled itself. Make the shelf 12 inches deep and shorten the bracket, and it triples. And that's static. Real life is not static. You don't set a coat on a hook. You throw it and yank it back off. That yank is a shock load, and a shock load can spike to several times the resting weight. Every one of those yanks crushes the gypsum around the anchor by a fraction of a millimeter. The hole gets a little bigger, the anchor gets a little looser, the wobble gets a little worse, and the whole thing works like a wrench backing out a bolt. Anchor failures almost never happen the day you install them. They happen 8 months later, and people blame the anchor. So the honest summary is this: drywall anchors are fine for flat, light, static things. A picture frame, a thermostat, a smoke detector, a towel ring maybe. The moment something sticks out, gets touched, gets pulled on, or holds real weight, you're asking gypsum to do the one thing gypsum cannot do. The answer isn't a better anchor. The answer is to stop attaching to drywall at all. Here's the technique. It's called a mounting plate, and it's a piece of wood, a second board fastened flat to the wall, screwed through the drywall into 2 or more studs that bridges from stud to stud and gives you one continuous surface you can put a screw into anywhere along its length. You've seen 1,000 of these and never registered what you were looking at. Every coat rack with a long horizontal backer board is a mounting plate. Every kitchen wall cabinet has one built into it. That thick rail across the top of the cabinet back exists so the installer can hit studs wherever they land and still put the cabinet where the layout says it goes. Every French cleat starts as one. The concept is completely ordinary in the trades and almost never explained to homeowners, and it's the single highest leverage idea in home mounting. Because look at what it does to the numbers. The published design value for a number 10 wood screw in spruce pine fir framing is about 95 pounds of withdrawal resistance per inch of thread embedded in the stud. And that's already an allowable value with margin built in, not a failure load. Run a 2.5-inch screw through a 3/4-inch board and 1/2-inch drywall, and you've got 1.25 inches of screw in solid wood. Call it 100+ pounds per screw, straight pull, with a safety factor already applied. Put 4 screws in that plate, and you have several hundred pounds of allowable capacity where you previously had a 60-pound anchor. And in shear, straight down, which is how most loads actually act, wood and screw are stronger still. But the capacity isn't even the best part. The best part is what the plate does to the leverage problem. Remember that shelf prying its top fastener out of the wall? Screw the shelf bracket to a mounting plate instead, and the pry force at the top goes into a screw buried in framing, while the bottom of the assembly pushes back against the wall across the entire face of that board. Gypsum's one genuine strength is compression, and a 3.5-inch board spanning 3 feet gives you over 100 square inches of bearing surface. You've taken a concentrated prying force and turned it into a tension load the framing can trivially handle, plus a compression load spread so thin the drywall doesn't even notice it. That's the whole trick. You're not making the anchor stronger, you're changing where the force goes. Now, how to actually do it, because a few details separate a plate that works from one that sags. Start with length, and this is where most instructions get it wrong. Studs are on 16 or 24-inch centers, and a stud face is only 1.5 inches wide. If you cut a board 18 inches long and hold it up in a random spot on a 16-inch on center wall, you are not guaranteed to catch 2 studs. To guarantee 2 full stud faces on 16-inch centers, you need at least 17.5 inches. On 24-inch centers, which is extremely common in garages and older construction, and on 2x6 exterior walls, you need 25.5. Don't guess which one you have. Measure between 2 confirmed studs before you cut anything, And honestly, 2 studs is the minimum, not the target. 33 inches gets you 3 studs on 16-inch centers, and 3 studs is where a mounting plate stops flexing and starts feeling like part of the house. The wood is nearly free. Cut it long. Thickness, 3/4 inch minimum. That's a 1x from the lumber aisle or 3/4 plywood. Same thing dimensionally. Thinner than that, and the plate itself becomes the weak link because a thin board flexes and lets the hardware pry against it, which puts you right back where you started. Plywood is the better choice structurally. The cross-laminated plies resist splitting when you drive screws into the field of the board, and there's no grain direction to work against you. Solid pine is easier to make look nice. Hardwood is the strongest and the most annoying to drill. What I would not use is MDF or particle board. No screw holding in the edges, it creeps under sustained load, and one plumbing leak turns it into oatmeal. Width, at least 2.5 inches, and 3.5 is better because you want room for 2 screws per stud, one above the other. That matters more than people realize. 1 screw per stud is a hinge. The board can rotate around it, and the more your hardware levers on it, the more it works that single screw loose. 2 screws, separated vertically, turn rotation into a couple that the framing resists. 2 screws per stud is the difference between a plate that stays put for 20 years and one that's loose by spring. Finding the studs. Use a magnet. A strong rare earth magnet dragged across the wall will grab on the drywall screws, and drywall screws are driven into studs. Find 2 or 3 in a vertical line and you've got a stud, not a guess. Then confirm the spacing. If your marks are 16 or 24 inches apart, you're reading the framing correctly. If they're 11 inches apart, you found something else, like a pipe strap or a corner build-out. And before you commit, drill a 1/16 inch test hole at your mark. Wood shavings means stud. White powder means you missed. That hole disappears under the plate anyway. Now the safety item that almost nobody covers, and it's genuinely important. Electrical code says that when a cable passes through a stud, the edge of the board hole has to sit at least 1.25 inches back from the face of the framing. That rule exists for exactly one reason: to keep wire out of the path of fasteners driven from the finished side. The code is quietly assuming your screws stop at 1.25 inches. A 3-inch screw does not stop at 1.25 inches. Through 3/4 board and 1/2 inch drywall, a 3-inch screw buries 1.75 inches into the stud, and a 2x4 is 3.5 inches deep, so that screw tip is arriving at the exact center of the stud, which is precisely where a hole for Romex gets drilled. Same story with water lines. So, use 2.5 inch screws as your default. That gives you 1.25 inches of penetration, keeps you inside the depth the code assumes, and still buys you 100 pounds of allowable holding per screw. Go to 3 inches only when you've thought about what's in that bay. And regardless of screw length, be deliberate about the vertical zones directly above and below outlets, switches, light fixtures, and anything on the other side of that wall. Those are cable highways. If your plate has to cross one, shift a screw a few inches sideways. It costs you nothing. On fasteners themselves, do not use drywall screws. They're deliberately hardened so they drive fast and don't strip, and hardening makes them brittle. Under a lateral or bending load, they don't deform and warn you, they snap clean, and they do it without notice. Use a number 10 wood screw, cabinet screw, or structural screw with a washer head or a pan head. The flathead matters more than it sounds. A countersunk screw driven into a 3/4 inch board is a splitting wedge, and in a narrow plate it will start a crack along the grain. A washer head bears on the surface instead of trying to spread the wood apart. Drill a clearance hole through the plate. a hole the screw's threads pass through freely, not a pilot. This is the step people skip, and it's why plates end up standing proud of the wall. If the threads bite the plate on the way through, the screw jacks the board off the wall instead of pulling it tight. Clearance hole through the plate, pilot hole into the stud if you're near an end or working in hardwood, and the board sucks down flat. Hanging it. Mark your level line, drive one screw, check level again. One screw is a pivot and boards move. Then drive the rest working outward. Snug, not gorilla. If you crank on it, you'll crush the gypsum under the screw heads and dish the board. And if the wall has a bow in it, don't try to pull the plate flat against a wave. Slip a shim behind the low spot, or the plate will bow and the top edge will kick away from the wall. That's it. 15 minutes, one scrap board. Now here's what you can do with it. And this is where it stops being a trick and starts being a system. The obvious one, hooks, anywhere. Not at stud locations, anywhere along the board. Tools, coats, hats, extension cords, bike gear. Want to double it? Put a second plate above the first. Rip a 45-degree bevel down the middle of a board, and you've got a French cleat. One half on the wall, the other half on the back of whatever you're hanging. The bevel means the load pushes the piece into the wall rather than pulling it away, and it gets tighter the heavier it gets. And it lifts off in 2 seconds when you want to rearrange, repaint, or move. Cabinets. You already know this now. That hanging rail across the back of a wall cabinet is a mounting plate, which is why the cabinet can go where you want instead of where the studs are. And when you're installing, a temporary plate screwed to the studs at the bottom line of the cabinets gives you a shelf to rest the boxes on while you fasten them. That single trick makes solo cabinet hanging possible. Built-ins. Small plates behind shelves and under tops do 3 jobs at once. They stiffen the shelf against sag, they add square corners that keep the unit from racking, and they give you a surface to screw through into the wall. TV mounts. A plate behind the bracket lets you center the TV where you want it instead of where the framing lands. Paint it the wall color and it vanishes. Grab bars. And this is the one where the industry already agrees with me. Accessibility standards require a grab bar and its mounting to withstand 250 pounds applied in any direction. There is no drywall anchor that does that honestly, which is why code-driven construction puts solid blocking in the wall before the drywall goes on. If the wall's already closed and the studs aren't where the bar needs to be, a plate spanning studs is the retrofit that gets you there. That's not a hack, that's the commercial solution. Steel stud walls, which are increasingly common. This is where mounting plates matter most, and almost nobody knows it. A 25-gauge steel stud is 18 thousandths of an inch thick. 18 thousandths. There's nothing there for a screw thread to grab. The standard fix in commercial work isn't a bigger anchor. It's a wood ledger spanning 3 or more studs, so no single flange takes a concentrated load, which is exactly what we've been describing. Plaster and lath. Plates are a gift here because plaster punishes you for every hole you drill. A plate lets you make 4 carefully placed holes into framing instead of a dozen anchor holes into brittle plaster. Just verify each stud individually. Pre-war framing spacing is a suggestion, not a rule. And it doesn't have to look like a garage. Rough plywood is fine in a shop, but run a roundover or an ogee on a piece of clear pine, prime it, paint it the trim color, and what you've mounted reads as a piece of trim. A mudroom rack, a hallway hook rail, a shelf ledger. It looks intentional because it is. One limitation, honestly. The plate itself is a beam. If you hang something very heavy in the middle of a long, narrow plate, the board will flex between studs, and a flexing plate transmits that movement into the drywall behind it. For heavy loads, either put the hardware near the screw lines or step up in width and thickness. A 1x2 spanning 24 inches with 100 pounds hung at the midpoint is not the same as a 1x4 spanning the same distance. So the shift I'd like you to make is this. Stop asking which anchor is strong enough. Anchors ask the weakest material in your wall to carry the load. Ask instead how you get that load into the framing. And once you're thinking that way, the answer to "there's no stud where I need one" is never an anchor. It's a board. Wood is cheap. Studs are already in the wall. All you're doing is building a bridge between them. And if this changed the way you look at a wall, go watch the rafter layout video next. It's the same idea, one level up. That one's about how framing gets laid out and cut in the first place. And once you can read structure instead of guessing at it, you stop wondering where a house is strong and start knowing. Then tell me down in the comments where you've used a mounting plate in your own place. That's where I get most of my best ideas.